For the introduction. Welcome to this presentation. I'd like to introduce you briefly to the iProd project, since this is the first lecture of the iProd mini symposium, with the 3 sessions that I reintroduced. iProd is a project related to the integration, the intelligent management of heterogeneous data, of product heterogeneous data, and has the scope and the objective to create a software platform that could federate different tools that are normally present in the product development process in a company, in aerospace, automotive, and other type of markets, including home appliances, to capture and formalize the knowledge about the product and the process that is developed in the product development process. So this type of information, this type of knowledge is normally retained in the brain or in the expertise in a number of fragmented type of pieces of information. The iProd project has the mission to create a framework that could collect and unify and link all these pieces of information and make them operative, so that knowledge can be retained and reused to shorten the time to market and the development cycles. What I'm going to present now, it's just a small part of the project, and you will see that the project is rather broad and complex. Different parts of the project will be presented along the different sessions. Tomorrow there will be a session that will explain a bit more in details what is the broad context where iProd was born, what type of problems it addresses, etc. So, coming back to the presentation of today, my position in LMS is to coordinate the part of coordinate the project execution from a very high level point of view. Thing that could not be possible without the support, active support of all the partners and the work package leaders. I'm now presenting specifically a topic on which I put my personal contribution, which is the process integration and design optimization ontologies. That is a topic which is also very close to noisy solution, which I'm also representing today. So, why process integration and design optimization ontologies for next generation engineering? I think that this comes from the observation of some trends in the process integration and design optimization research and the ontology market, the ontology field. There are a number of challenges that engineering is now facing. These are pretty clear to most of us, have been discussed also in the previous session, so I'm not going to repeat them too much, except link them to what has been done in the ontology part. So iProd took the way of using ontologies to create concepts and relations between these concepts that have a special focus on the product development process. So this is an ontological approach to the product development process, and it's exploiting a number of research that has been done in the ontology field. In particular, in the engineering field, it is to share common understanding of information between people and software agents. This first bullet is per se a big challenge because this means that first you need to attribute a meaning to what you are doing in engineering, to the different phases, activities of the product and the process that is associated to the specific product. And after you have associated a meaning, you should build relation between the different concepts that you have created. So in this way, the objective is to enable the capturing of knowledge, expertise, and a number of guidelines, best practices, lessons learned into a knowledge store that implements the concept relation paradigm. This for a clear purpose, which is the reuse of the domain knowledge, not of a generic knowledge or a general purpose knowledge, but of the domain knowledge, the company knowledge even. That is something that stays within the company, stays within the aeronautic, automotive, or other domains, and is exploiting the peculiarities of this domain. This is, however, not focusing or verticalizing too much, because it's inheriting from procedures, concepts, and relations that are common to many, if not all, engineering fields. I'm trying to go there. I will explain this a little bit better later. So once you make reuse of this domain knowledge, that is, make sure that design decisions are not lost, that mistakes are not done 2 times, that the product improvement process, like we were discussing yesterday, it is kept, it is keeping the knowledge progressively among the different phases. So this also needs to, aims at making the domain assumptions explicit. A number of things that we know by experience sometimes are not written, but it's just our understanding, our good practice. Then this should be made explicit, because tomorrow, when the new engineer will graduate and come to the company, needs to not repeat again the same mistakes that I did when I entered the company, I don't know, 15 years ago. So this type of knowledge needs to be made explicit and available. Another topic is also to separate the domain knowledge from the operational knowledge. What is something that is common to a specific domain, so like knowledge about certification rules, knowledge about how products are structured, how products are classified, how the processes to build these products are generally applied, from the operational knowledge that is much more closer to the daily use of the tools, like doing an FE computation or assembling FE computations from multiple disciplines, as well as doing manufacturing. So all this knowledge about, I don't know, tolerances. Yesterday we were having an interesting discussion during the presentations of one of the sessions about bringing knowledge along the process on one side, but also collecting it from the field, from the expertise of the people, and building robustness inside the process. So I believe that this is very related to that topic. And then capability to analyze the domain knowledge. Analyze, it's not only mine the knowledge to gather something, but also exploit the knowledge to build something that can be new or implicitly new. Maybe a small achievement that was done in a field that is similar and that can be applied in another thing, or that combination of technologies that we have not yet thought about, but that they are both available in the company that can be used together to solve specific problems. A very simple example, if we go down to the earth and speak about simulations, which will be also one of the topics of today, is, for example, that I'm preparing my model on my computer, and the simulation is running on a cluster that is not in my administrative domain even, probably. Then it's clear I can inference that I need to transfer, I have to make an operation to transfer this thing to the cluster, run it with some permissions, some constraints, etc. This type of knowledge, which is absolutely obvious to us, it's impossible to be explicitly derived by a machine. Well, there have been work in the iProd consortium to make this knowledge explicit. So to infer a number of operations which are obvious to us but not to the machine, and make the procedure stable and exploit the knowledge. So a lot of these items that have been part of the ontological research in the past years have been exploited in the project with the objective to build the ontological framework, the knowledge framework, to speed up and improve the product development process. So the challenges that we would like to address are related to, I would say, three main pillars. One is capability to solve, or I would say address, complexity. This because of the inherent, the implicit complexity that nowadays products are having. If we think about turbines, but even internal combustion engines, or systems or subsystems of satellites or of other devices. I mean, all these systems and products are becoming always more and more multidisciplinary, interconnected, multi-physics, and need a lot of information to interoperate with each other. So I would say this is increasing the complexity and the dimensionality of the problem. Together with this, if we increase complexity, we increase at the same time also the heterogeneity of the information that is included in this complexity. So this means, for example, different type of tools, different type of data, different type of information and meaning that this information has. And everything has to be interconnected or interfaced somewhere. One of the things that I remember yesterday was discussed was that main issues, main bottleneck, one of the main bottlenecks in the implementation of a good development process is one of the bottlenecks was related to interfaces and to building a common understanding of what needs to be done. That is shared and that can be implemented by everybody. So in this way, in this case, it's a kind of addressing the heterogeneity problem, which can go very simply from Word and Excel files up to complex CAD models or manufacturing data. All these things should cooperate, should be exploited. It's data that is sitting there and not being used. And then possibly execute it efficiently, not only from a point of view of the simulation or the modeling. We've spoken a lot about the modeling thing, but also, and I would say, essentially on the overall life cycle of the product, which includes manufacturing, voice of the customer, end of life cycle phase, as well as the preliminary phase, even conception things. So these things need to be executed efficiently and exploit horizontally along the product development process and vertically down to the details of the computational aspects or manufacturing aspects, all the information and the resources that can help in this direction. It's a pretty ambitious challenge, but if we generalize to the highest level possible, essentially these are the three main problems that I see need to be addressed to really build up the right knowledge formalization. So PIDO tools are addressing only a part of this whole problem, or maybe we can say an instantiation or a particularization of this problem into the simulation phase, which is normally going from the preliminary design to the detailed design and pre-verification. So it's part of the typical V diagram that we all know quite well in the product development process. The PIDO tool is a tool that is aimed at federating and integrating the knowledge that is contained in a number of tools that we normally use, and has the objective to let them interface or interoperate within themselves. So it's already by nature, without the need of using ontologies or knowledge mapping techniques, is already a federating tool, and it's facilitating this approach of the federation. However, the challenges that we are now facing with the increasing complexity, increasing heterogeneity of data, and the need to make all this always more and more efficient, so not to increase the time to market, but rather to decrease it, is evolving the process integration design optimization paradigm to something that I believe is split in three main blocks. So traditional PIDO tools are now evolving in my view, towards frameworks that federate simulation, towards algorithms and methods that can handle large-scale optimization and design improvement processes, and exploit as much as possible for the simulation part HPC and virtualization with hybrid clouds, with a number of tools that now are emerging always more and more. So, point that is related to these three new areas where the process integration design optimization tools are going relates to federation, knowledge, automation, methodologies for high-dimensional and multidisciplinary systems, and virtualization. So delocalization of of where the execution takes place. Why we would like to introduce ontology in this context? PIDO is already a well-consolidated tool. It has been used. It is being used a lot. It is part of large deployments. Why we'd like to introduce ontology there? One of the motivations is that ontologies enable all the things that I said at the beginning that now the PIDO tool does for a small percent. Essentially, the main objective is to capture the knowledge related to the simulation process and the design improvement processes by giving meaning to this knowledge. So to find a way to describe and tell to the computer what this simulation process is about and why it is about it, and how I got there, why I'm using this optimizer rather than another, and why it is linking these disciplines rather than others. So build this explicit knowledge associated to the workflow, to the simulation process. This approach is being developed and tested within the iProd project, to which these sessions are dedicated, and is exploiting a description of the domains that is also addressed by the project itself. So within the project there are tasks related to mapping domain and knowledge that we are addressing. In particular, we are addressing aerospace, automotive, and home appliances domain that have characteristics that are pretty different in terms of number of products, complexity of these products, and technology content of these products. So with aeronautics, that normally has volumes of products that are relatively smaller with respect to automotive, but with a much higher technology content in general, and with automotive, which is definitely a consumer product, so with a large production process, but with the technology content that is definitely lower than an aircraft and higher than a fridge or a washing machine. And on the other side, home appliances that have a huge production, huge number of products. I believe more than cars, with a technology content which is definitely simpler, which can go from the just simple aesthetic design down up to the complexity of, I would say, a washing machine or a blender. So context is pretty broad and domains pretty different between each other. Objective is to address all of them. I will try to explain how this works for one of the use cases that we have within the project, highlighting that the main benefit that we would like to have with the application of ontologies is combine the advantages and that come from all the tools that are part of the product development process. So normally when you chain all these tools and when you put all of them together you are building knowledge that is in the process of how to change these tools, what is the sequence, who are the experts, why it's done in this way. And this knowledge sometimes is partially captured by business processes, but up to at some point business processes then stop. They don't become operative. I mean, it's up to the user, to the engineer, to make them operative. There will be a task that says, build a model with these constraints, with these properties, and optimize it. But the specific, concrete actions are not always taken. And the results are not always easily fed back into the system to pass to the validation and verification phases. So this is something that may become a bottleneck. The idea is to use the relations and the knowledge to facilitate this homogenization of the product development process from the top level, the high level engineering activities and business processes down to the simulation steps or to the machine oriented steps, and automate it if possible as much as we can to gain time. So an ontology, I believe that most of you know what it is. Just to have a common understanding, is a description of a domain in terms of concepts and relations. These relations can be explicit or implicit, so it can be made explicit or derived by inference. In this way, we call generically the knowledge and information can be normally found easier. The meaning that we have attributed is easier, and not create an overhead on top of the engineer, an excessive overhead on top of the engineer that is putting this knowledge in the system, not more than defining the simulation process itself. So one of within this context, the first thing then, of course, to do is to build an ontology. So to build a set of concepts and relations that that can interoperate between themselves and that make explicit. Oh my God, it's probably too small from there. So I can read a little bit from here. So a set of concepts and relations that that can be made operational and formalize this thing, the knowledge about the simulation process. So we have two, I said. One is the process integration ontology, and the other one is the design optimization ontology. The process integration is aimed at capturing the what of the simulation process, of the analysis process that you're doing. So what you are capturing, which disciplines, at what level they are structured on top of each other, and what is the sequence or the parallel branches. So we start from a simulation project that has simulation workflows in it. Each simulation workflow is made of workflow elements and workflow methods. And each workflow element can be of different types, and each different type have different relations between themselves and with the other concepts. It's not only a way to structure the information hierarchically, but it's a way to build knowledge about how this information is related to each other. There are standard relations, some others are specific, like having inputs, having outputs, and it's normally based on a paradigm which is a definition of inputs, pre-processing, analysis, post-processing, and outputs. So this approach is generally applicable. It's implementation independent. It can be good for eyesight, it can be good for Optimus, it can be good for another process integration design optimization tool. It's absolutely neutral because it's dealing with knowledge, not the tool itself. So this captures the what. Then the design optimization part on the other side captures the how. How we perform the analysis and what are the methods that can be applied to analysis. So how to structure or define methods. So we see here that, yeah, well, actually you cannot see, but you can believe me, there are workflow methods that are methods or description of how we can use this workflow for something. So can this workflow be used, for example, for CFD optimization or for CFD analysis? Can this workflow be used for structure analysis? If yes, in what conditions, etc. So these methods can be associated to, we call it generally optimization, but more broadly are iterative or design improvement methods. That are defined in this way, starting from a process, which in its turn inherits from the business process definition. So it's still aligned and compatible with the business process modeling notation, which is a way of formalizing knowledge about the processes, and extends these concepts with methods, algorithms, problems, definitions, characteristics of the problem, components of the problems and of the algorithms, and links to simulation workflows. So in the knowledge about what and how it's linked, it's made explicit, can be derived and used within the context of engineering. Starting from a small thing and then expanding and building up to more complex products. This is not, I would say, a top-down approach, neither a bottom-up one. It is something that can be started in islands and will automatically connect once more information becomes available progressively. The innovation aspects that we gained with this approach, which is being developed and with some prototypes, a couple of slides I will show you one prototype, is to create, manage and link the conceptual models on one side, make these concepts operational, so make them work for you, and possibly avoid conflicting processes, detecting inconsistencies, detecting bottlenecks, or places where these slow down. For example, inconsistencies with requirements, or inconsistencies with your IT environment, your capabilities, the tools, the methods, the things that you can do with this simulation process. So it's a way to streamline and make the whole analysis step, at least for virtual analysis, the most straightforward thing that one can do, without having to reinvent the wheel every time or rebuilding always the same workflows every time. It's also a way to dynamically navigate the ontology and say why I use this method to solve this problem, why I use this approach, and why this solution is good or bad. Why this, for example, this morning we were discussing about the optimization processes. Some of these optimization processes yield solutions that can be just too good to be true. I mean, it's one of these situations where you as an engineer immediately recognize that something was missing, or that cannot be used by another department. Then in this way, these links can be mapped, can be built. But also to build the bridge between nice formalization and the concrete down-to-earth engineering tools. So then get physically to the tool. One of these aspects will be demonstrated also later in the second session with a live demonstration. There will be one of our partners that will demonstrate how this goes down then to the physical problems with a live demo. Clearly, the main goal is to build what is known to be the unique source of truth. So the place where all the knowledge about product and process is considered formally correct and usable.